Question 14, we're going to do this one really quick just because we went through the first example quite thoroughly and we're going to go through question 15 quite thoroughly. So in this one, the mass in grams of a radioactive substance is initially 20 grams. So initially, now that's our first thing, initially 20 grams. So that first piece of information is when T is equal to 0, T is equal to 20. The substance has been stored for 30 years already. The mass in any year is given by this expression where MO is a constant and T is the time in years. Determine the value of MO. Now, MO is when we get our value and we substitute in 0. That's like a little fun way of noting it at the same time. And it's saying that because here we don't have a constant, it's saying that its initial value is going to be the same as MO. And this is what I was talking about in video 13, because people get confused and think like, oh, okay, that's always the initial, but it's not always the initial. It depends about whether or not there is an asymptote. Okay, so let's just go straight in. Determine the value of MO. So we're going to substitute in when T is equal to 0, M of O is equal to 20. So 20 is equal to MO, E minus 0.00152, and that's 0 as well. Now anything times 0 makes 0, so E to the power of 0 is going to be 1, meaning that MO is equal to 20. So therefore, our model is now going to look like this. T. So that's what our model looks like now with the information that we calculated earlier substituted in. So calculate the amount of substance remaining after a further 30 years. So that means that T is equal to 30. What is our mass at that point? So let's substitute that in. So M30 is equal to 20E minus 0.00152 times 30. Okay, so go over to my calculator, chuck that in straight away. So that gives me 19.11 grams. Assuming that this thing is in grams. Yep, mass every year. Okay, so after 30 years, there is 19.11 grams. And now the next thing we need to check is whether or not that is decaying or not. So the mass of a radioactive substance is initially 20 grams. The substance has been stored for 30 years already. The mass in any year is given by this. So this is the mass. So at 30 years, 19.11 grams remains. Now, it's important to be careful about reading these questions because sometimes when they're asking you something in this section, they'll say how much has decayed. So if I wanted to know how much has decayed, it's very tempting just to throw everything in and then leave it. But if I was to work out the decay, then that means that I need to do the 20 minus this, and then that would tell me how much has decayed after the 30 years. Okay, part C, we're going to determine the rate of decay. Now, I've seen the word rate, which means that I'm going to be calculating M-T. So, we're going to calculate the derivative of our function at the time when it's 30. So, it's asking you at this time, which means at that time. So, let's chug it straight in. If I calculate the derivative of this function here, it's going to be equal to this. So it'll become 20 times negative 0.00152 bracket e to the power of negative 0.00152 t. Now the next thing I'm going to do is I'm going to chuck in my number 30 into the position that t currently holds. Now I'm just going to go up to my original one, go back. So negative 0.00152 times 20. Now, that'll give me the same thing that I want. So it's going to be decreasing at a rate of 0.029 grams per year. Okay, and the reason that I can tell this thing is decaying is because initially we had 20, it's decreased to 19.11. And then down here, this should give me a negative if it's decaying. If I graphed this thing, here's my initial value, there's 20. So that's when t is equal to 0. Over here, when t is equal to 30, we've gone down like that, which looks like that. So if I then try and calculate the gradient at this point, it's got a negative gradient, so that should be reflected down here. If we're rounding to 2 decimal places, then this should be 0.03. And that's your question.